All right. Hello, everyone. How are we? Happy Tuesday, all that jazz. Few logistics things. I guess it's always good to remind you all the exam is in 3 weeks. Whatever. It's a good ways away, but just so you don't forget it exists. And the thing I want to mainly talk about is I did finally look through the survey. So I'm going to show you all the results of the survey results. Don't worry, it doesn't have anyone's name on it or anything like that. Sadly, it's actually impossible for me to get people's IDs matched with the responses. And I was hoping with this file to pull it out and then do correlations between how much of the problem sets to how people did on the tests and things like that. But sadly, that's impossible for me with this build, which is annoying. But I am going to kind of show you all some things just because I think it's interesting. I think it's useful for you all to see this. So the first question I asked you all, again, don't worry, it's not going to show individual responses. I also want to point out there's not a right answer. It says that this is the right answer. All of these were worth points. You hopefully saw that. When you finished the survey, you got the 2 points no matter what you picked. So don't worry about the correct or incorrect. Ignore that. I just have to pick an answer as correct. In fact, here, let me just show you all. Look, for this first question, just to make certain all of them are worth 0.4 points, I just have to pick one as correct because I don't know why. It makes me. All right, so to that end, I just want to show you all some of these things because I think they're interesting for you as much as they are for me. So here we have whether or not you've taken physics before. The reason I asked this question is because hopefully this class is easier for you if you've seen physics before. So I wanted to kind of pull this information and then see how grades compared for those that have taken physics and those that haven't. But the reason I'm showing you all this, if we collapse the university level and the AP level, so we collapse that into the AP, it actually splits into thirds pretty closely. About a third of people have taken some college level physics before, AP, IB, university. A third have done standard or honors, and about a third have not taken physics. Why do I mention this to you all? Why am I showing you this information? I'm showing you this because for some of you this is going to be easier because you've seen it before. So you would probably fall into the AP, IB, university level. On the other end is people that have never seen physics before. And I wanted one, if you've never seen physics before, that's not an expectation going into this class that you have seen physics before. I don't expect that. And that is a lot of you all. That is a little over a third of you all have never seen a physics class before. And that's fine. I want to mention this to you all because 2/3 have. And the reason I say that is if you look around like, man, why is this coming so much easier to someone else? If you ever feel that way, it could be because they've seen it before. And so to that end, it's not a knock on you as a person. Of course, it's easier for someone else if they've seen it before. So it's to help give you a frame of reference that it's okay if this comes easier to other people and harder for you, especially if someone has seen physics before. So it's to give you maybe some peace of mind that there is variation. And this is true of every class you all ever take. If you all take an intro to C class, some people have programmed before, and it will come easier to them. So that is true of anything in life. And it's never good to say that everyone is the same as you. And that goes both ways. If someone's doing better than you or someone's doing worse than you, there's variables outside the class that affect those things. It's not all purely just how smart, in air quotes, you are. So that's a good reminder. All right. Next, this is just kind of interesting. How did they rate the difficulty of the kinematics portion? So you can kind of see how it felt for you compared to other people. So here's the distribution. We can see that the average is probably around like a 6. 6 out of 10 difficulty, maybe a little bit less than that. Which if I had to guess, I would have guessed like a 5. So that's, it's in the ballpark of that. If it was more difficult for you, that's fine. If it was less difficult, again, it's not a bad thing or a good thing. But again, it's just interesting to see how you compare to other people, how you perceive these things. What is good for me, this is all good knowledge for me. The distribution looks almost identical for the force portion. So that's nice. That means that there was like consistency, different topics, but the difficulty levels seemed to uniform across the test. That's good. That's one of my goals, is that if I teach you all these things, that the concepts feel a similar level. And then this one's just kind of interesting, kind of how much did you go through the problem sets beforehand? And you can kind of see here the distribution. It varies, maybe on average 60% of them or something like that. I don't know. But again, it just gives you a sense of how people prepare and things like that. If you're on the lower end, it's maybe one of those, maybe I should, and if the test didn't go well, it's like, okay, maybe I should, whatever. You pull from this what you think is interesting. I pull from this kind of just gives me a sense of how people are preparing, if people are using the resources. Again, I would have loved to have made a correlation of this with test scores, but it's impossible for me to pull this data and see individual student responses, so I can't match it to test scores, so I can't do that analysis, which is sad for me. I wanted to see if my problem sets were useful, but I can't do that. So here we are. All right. And then how prepared did you feel going into it? There you are. People largely felt prepared. We're on this end of things largely, so that's good. Just interesting to see. Again, you take from it what you may. I have my educational reasons for collecting this stuff. It gives me feedback. And then at the end, and I'm not going to pull this up because there's like 193 responses, which I was very excited about, was the written feedback, which I got a ton of feedback. Oh, sorry, I forgot the duck. 2 people mentioned feedback of bringing Demo Duck, and I forgot to bring him today. Yeah, I forgot to. Someone actually in office hours was like, can you bring him to class? And I was like, sure, and then I forgot. So that's my bad. So I'm going to give you all the 2 changes I am going to make, the 2 things I'm going to try to do to help you all, and then I'm going to tell you one thing that was asked a lot, but I'm not going to do, but I'll tell you all the reason why and teach you reasons why. So the 2 things I'm going to do, one of the things was working out problems entirely. So I often get to step 3 with you all in problems, and then I don't do step 4, plugging in the numbers, and that's kind of the last thing. So I will start to do that. I will do that last step, and it doesn't take too long. And that way you all have the entire completed problem that we do, and you can see what it looks like to do that last step, step 4. I'll do that. The second one was like almost like a bank of conceptual questions. What I will do there is I will, as we get close to the test, I will take all the clicker questions from all the PowerPoints, and I'll copy and paste them into a new PowerPoint, and I'll post that for you all. So they're all already available, but I'll make it in a nice, organized way for you all to check out. May or may not add a few extra questions for you to look at. When I pull them over, I'll have the answer inked, so you can hide the answers or see them really easily. So I'll do those 2. One of the most, because those are fairly common, and I agree that those would be useful things for me to do. One thing I heard a lot of requests for, and I'm not going to do this, but I'm going to tell you why, is fully worked out solutions to every problem set problem. The reason I'm not going to do that is not because of how much effort or time it takes. It's actually, I'm going to show you all, it's really easy to generate worked out solutions to these. The reason I'm not doing it is, there's 2 reasons. One is sometimes people fall into the trap of only looking at worked out solutions to solve a problem, to see it, to prepare. They'll just take the full worked out solutions, just kind of look through and say, that makes sense, that makes sense, that makes sense, that doesn't make sense. And there is some benefit to that, but it's kind of like looking at someone else do a painting and saying that makes sense. If you've ever tried to paint, if you ever watched a Bob Ross video, he makes it look really easy. I've never tried to do it myself. He says it's easy, but how do you figure out whether or not you can do it? You got to actually do it. You got to actually work it through. And the reality is you got to work it through without a worked out solution in front of you, because otherwise you're not learning the skills, because ultimately on the test, there's no worked out solution in front of you. So anyway, that's one reason. The other reason I don't have the worked out solutions is almost half of your college degree, half of the value of it is some of the college degree shows that you can learn things on your own, which sounds rough. I say learn things on your own, given a problem. So in your job, you're going to be given a problem. They're going to say, I need you to build a part that does this. Do it. And they're going to leave you there. That's not going to be the thing. Maybe in the beginning they train you and they do some examples and stuff like that. But most of your all's job is going to be given a task that you have never done before, potentially. or maybe done something like it, can you learn on your own how to solve that? Can you figure out what resources to find? So basically learning how to learn, learning how to find good resources, learning how to use existing tools out there. An easy example of this is programming. If you've ever programmed before, every single programmer has Google open in a new page. At least that's how it used to be back a few years ago. Now, building on every good programmer knows how to Google things really well. That's true of you all in like every class you all take. Any engineering stuff, learning how to use the internet to find resources to solve problems that don't have a solution yet. So 3 years ago, I would have said, get good at, you need to become good at Googling things. You need to get good at finding YouTube videos that have stuff related to it. It's like if you need to fix your car, can you do it? Can you find a YouTube video for how to change your brakes kind of thing? I've never changed my brakes, but those are skills that's going to separate you in the workforce is can you actually find those resources as opposed to me just kind of giving you everything in this class and you never having to look outside this class. So anyway, to that end, one more thing I'm going to encourage you all. You now live in the age of AI, for good or for bad. And I told you all making worked out solutions to every problem would totally have taken me a while before this. But I'm just going to pick a random problem. Great. I haven't even taught you all this momentum. Yep. Just going to pick a random problem. If you ever want a worked out solution to something, you can now, ChatGPT exists. And this is a skill and a resource that you all need to learn how to use in today's day and age. Because it exists and it's incredibly useful. So behold, as it generates a full worked out solution to the entire thing. Now, again, be careful with this. Don't just use this for every single problem and don't try it yourself. But if you're stumped, so I just put the entire problem in here and did it spit? Nope, still working. The beautiful thing is I give you all the answer. One of the things when you all use AI, you need to ask yourself, is this correct? If you all assume that it's always correct, it's not going to go well for you. It's correct. It's fairly good, but you need to learn how to evaluate whether the outputs of AI are correct. Now, again, you're lucky in my class because I literally give you the answer. There it is, the answer, 5.9. Oh, look, they spit out 5.92. Their process is probably correct. Their process was very likely correct, but using this resource, so I just did it the most basic way possible. I literally just put the problem and hit enter. I didn't even say solve this problem. I just put it there. You all can use this in all sorts of ways. Remember, there's multiple steps in the problem-solving process. What I can totally say is, what are the givens in the following problem? If there's a specific step that you're confused about, use this not to give you the entire thing and just say, yep, that makes sense. Use it to get the next step. Use it to get the step that you're stuck at. Because the biggest thing I'm training you all in is how to think. That's the reason I don't put the full worked out solutions and things like that. Learning how to think and learning how to learn kind of on your own. It sounds rough. Yes, I'm here to provide you resources and all that stuff. It's not me just abandoning you. Come to my office hours, shoot me emails at all the things. But the reality is you're going to end up in jobs where you're going to be given problems that might not have a solution that anyone has found before. And what are you going to do in those cases? Learning how to approach problems where you don't have a worked out example, where you don't have that stuff. What do you do? And that's a skill set that you have to develop. And that's why I don't provide the worked out solutions, because I want you all to develop that. I want you to learn how to find things that you don't have. So, anyway, there's a rationale there. And I say all this. If you ask me for that, that's not a bad thing. I don't want you all to feel bad if you're one of the people that asked, hey, can you provide all the work solutions? That is not a bad request. I wanted to give you all the reasons, though, why I don't do so. Not because your request was bad, but just because there's teaching reasons why. It wasn't just because it's a lot of effort for me. So I always want to clarify that. If you all have any questions about any feature in my class, let me know. If you all have any suggestions, I scrolled through the entire list of 193 of them and kind of looked through them. I really appreciated all the feedback. It is helpful for me to improve. Again, there is things I'm going to do differently to help you all based on that. So, there you go. That's my little spiel. Let's see. Any comments, questions, concerns about anything? Yeah.
Now that the free response parts of the exam are in,
Yep.
would there be a way that we could go and look at what we got wrong on our tests?
Yes, I do have all the free response tests. If you could, email me in advance that you want to see your free response because they're not alphabetical. And there's 293 of them. And so what I will do is if you want to see your free response, shoot me an email. And then hopefully, if enough people, I'll wait a little bit to get as many of those emails as possible. So when I go through one by one and find names, I have to do that as few times as possible. Because it just takes a little bit. But yes, I'm happy to do that. You just come to my office hours. I show you all. That's the kind of thoughts. Oh yeah, and free response grades are out. Overall, happy with them. If you have any questions about those, let me know. Anything else? Yeah. The 2%, yeah, that's a good question. Has the 2% from the survey been added? Yes. So you can check that for yourself. I have a portion of your grade that's from the free response. That's out of 20 points. I have a portion of the multiple choice that's out of 80 points. If you add those two numbers together and you add the 2%, you'll get the score for the exam 1 total. That's how I generated that. So there's a score called exam 1 total, and literally you just add all the points from the survey, the free response, and the multiple choice. It should add to equal that number, so that's how you can check that for yourself. In the off chance you think it's not quite right. Yeah. I will go over that one on Thursday. Yep. I still have one more makeup that due to hurricane and health reasons and various things. Thursday for sure, guarantee I'm going to go over the one question that 80% of people miss.
Hey, what's your joke for today?
Thanks. I always forget that. The joke for today, thank you for reminding me. I always get so caught up in the class. All right, I'm going to change this. It starts with a your mama joke, but to make it not your dog is so classless. I'm just going to change it to your dog is so classless, he could be a Marxist utopia. It's good. So classless, because in Marxist, there's no class system. Everyone's equal, but totally someone's got a rule like that doesn't work that way. Yeah, the duck's in my office. I'll make a note to bring him on Tuesday. All right. Okay, so I left you all with this problem. We started this problem last class. So last class, we started conservation of energy. And where is it? This right here is the most important. Oh, where's my pen? Oh, I left my pen in my. Okay, well, you all are going to get some hideous drawings today. I'm drawing with my finger. Yep, desperate times call for desperate measures, y'all. All right. This equation right here is the most important. This E, all my energy I start with, plus the work done, equals the energy I end with. All the energy I start with, plus the work done, equals the energy I end with. This equation, and be warned, it's with my finger, so give me some grace. I'll post nicer ones than this. I'll post the studio ones. I'm not going to post my finger writing. These two equations. Oh, this is terrible. All right. That's all you need to know for energy. Like those two equations. Okay. You do need to know the equation for kinetic energy, potential energy, do those. But this is the bread and butter. These two problems can basically, these two equations are all we're going to do to solve every conservation of energy problem. It's going to be great. All right, if anyone does have a stylus that they're not using, that will result in significantly better writing for me. If not, you're getting finger paintings. Let's see if it does. Oh, no, it's not detecting it. Yep. We tried. I don't know. This one's not a paired one either. It just doesn't like it. It's not conductive. Very sad. All right. Last chance. Otherwise, you're getting finger writing. Don't worry. I'm not going to post the finger writing, but you make do with what you got. All right. Let's try. Bust. Last chance.
Try it.
Hey, your classmate saved you. Thank you. Yes. All right. I just need to make certain. Thank you for your sacrifice. Yeah, I must have taken it. It's in my office, I'm sure. All right. So this problem I gave you all. We start with the clicker questions. I said, what energy do I start with? Because this is like all these conservation of energy. What do I start with? In this problem, we started with elastic potential energy. Bam, there it is. Then you ask yourself, what do we end with? We ended with gravitational potential energy. And we're going to use that to solve this problem. All right? So let's set it up. Let's start from scratch. So a massless spring has a force constant of 12 newtons per centimeter. The second you see centimeters, you should have almost like a reaction to that somewhere in your brain. Centimeters. You got to convert it. When the gun is aimed vertically, a 15-gram projectile, grams, that's another one that's got to like ping your brain, is shot to a max height of 5 meters. How much was the spring compressed initially? So what's given in this problem? We have K, which is going to be 12 newtons per centimeter. And my handwriting's still going to be a little funky because I can't rest my hand on it, but it'll be better than finger writing. Before I even move forward, you know what? Let's put all of them. The mass is going to be 15 grams. And then, how do I want to put this Y final? How do I want to word this? I want you all to put what Y final is. So I'm actually going to give you 2 tasks here. 1, you need to convert both of these. 2, you all need to figure out what the Y final is. Try it out. I'm going to clean this up a tiny bit. Give you all like 20 more seconds. All right. So the key to the first one is you got to convert centimeters to meters. And so the question basically comes in your head, do I multiply by 100 or do I divide by 100? There's 100 centimeters in a meter, so you got to make that decision. Which way do I go? You can do dimensional analysis. You could do dimensional analysis and say, oh, I need meters on the bottom. How many centimeters in a meter? That totally works. So, you could say, okay, I need to get rid of centimeters. I need meters on the bottom. How many centimeters are there per meter? 100. So we're going to multiply those and woo, that's going to work. That's one way. That's not actually, so that works. That's kind of a very systematic way. I instead go a different way, which is more conceptual. What does this unit mean? Newtons per centimeter. It literally means how much force is required to push a spring 1 centimeter. That's what the spring constant means. It's how many newtons to push it 1 centimeter. So then you just ask yourself, do I need more of that if I'm going to push it an entire meter, or less of that? You need more. So I multiply by 100. That's how I logic through these. Instead of doing dimensional analysis, I just think through what makes sense conceptually. If I were to push it an entire meter, I need way more force than pushing it 1 centimeter. So I multiply instead of divide. Whatever. Both ways get you there. Pick your poison. So to that end, that's going to come out to 1,200 newtons per meter. Fantastic. All right, 15 grams. You got to convert that to kilograms. We're not going to spend as much thought on that one. That's hopefully you've done this a bunch at this point. And again, I'll upload, the version I upload will be much nicer handwriting because I did it in studio before. So this is at least legible, but it's not ideal. All right, the height. If you said it was 5 meters, you forgot something. The final height. So if we look at our picture, here, where is 0 defined? All the way at the bottom. That's on purpose. Because that's where we start, which means our initial potential energy is 0, which means we don't need to worry about it. So where do I end? It's not 5. It's 5 plus D. It's very tiny. It's actually not going to change the final answer too much. The final answer is 0.0351. If you ignore this, it'd be 0.035. But if this spring was actually, if we compressed it more, if this thing went higher, lots of things, this could change the answer a lot. But it's an important thing to realize here. This is the benefit of pictures. You can see in the picture why it's not 5 meters. And this is also why it's important to define your 0. In your picture, define where 0 is. 0 height, and everything is measured with respect to that. If you're above that, it's a positive height. If you're below that, it's a negative height. All right, what are we solving for in this problem? We are solving for the distance. How much it gets compressed. If you all ever see a spring and there's a beginning and an end, it's conservation of energy. I can promise you that. If you all see a spring and something happens, it's conservation of energy. And to that end, if it's ever conservation of energy, you are going to use the equation that I mentioned before. So through the power of copy and pasting all this stuff, moving it over here. Yeah, let me. For which one? For this one? Yeah, so the reason we're multiplying by 100, we can see it in our dimensional analysis. There's 100 centimeters in 1 meter. So the centimeters will cancel, which will give us that meters on the bottom. And also the logic is it's how many newtons per 1 centimeter. So it takes 12 newtons to squish this spring 1 centimeter. So how many newtons does it take to squish this spring an entire meter? We got to multiply. Oh, is my number off? No, 12 times 100 is 1200, right? Yeah, that's good. Yeah, so it is multiplying. Yeah, but I can chat with that more if that's still confusing afterwards. So this is our bread and butter, y'all. EI plus the work done equals EF. That is our bread and butter, y'all. That is like any conservation energy problem. That's what we're going to be referencing. Now, we are blessed. There is no friction in this problem. There is no air resistance. There is no person pushing or pulling it. So in this problem, the work is 0. There is nothing outside of kinetic energy and potential energy. Those are the only energies present. If your problem has friction or someone pushing it or air resistance, then there is a W. Otherwise, everything can be contained within the energies. And so then you ask yourself what energies are present, and we already answered that. See if y'all can figure it out. See if y'all can build this equation. What energies are present in the beginning? What energies are present at the end? We've already kind of talked about that, but see it for yourself. And I'm going to move this down. There we go. Yeah, so work is the integral of force times distance. There's no force, so basically the only things that we consider doing work are friction, air resistance, anything other than kinetic energy, potential. So gravity is its own, it gets the energy to gravity. Yeah, so gravity is doing work, but we put that in the energy. Yeah. Yeah, that's a good question. Gravity gets its own term. It doesn't go in the work here. All right, so again, we've actually answered these in the clicker questions before. So what energy do I start with? There's only three options. There's only three options for energy. There's a spring potential, there's a gravitational potential, and that's kinetic. That's your checklist. Those are the only three options I'm giving you in this class. There's way more types of energy than that, but in this class, those are the only three types we're considering. In this class, there's the only three types. Spring potential energy, if there's a spring getting squished. Gravitational potential energy, mgh. Kinetic energy, 1/2 mv squared. So we just check what kind do we have. In the beginning, we only have a spring. We're at a height of 0. We define 0 where we start, so we don't have to worry about gravitational potential energy. In the beginning, we're not moving, so we don't have to worry about that. So initially, we only have the energy stored in a spring, which is 1/2 kx squared. In our case, how do I want to label this? I'll leave it here for now. Reminder to y'all, x is d. We'll see that when we do part 4. Here. You know what? Let's just put it here. In our problem, our spring is compressed by d. So I replace x with d. If y'all look at the picture, that's how much it gets squished. All right. Equals, what kind of energy do I have to end with? mg, you know what? Actually, let's put the original terms and then we'll plug them in. These are kind of the way they look on the formula sheet. Let's actually put variables given what we have. 1/2 kx squared equals mgh. That's kind of the equations for them. But those don't match any, we don't have h, we don't have values for those. What are we using instead? So it's going to be 1/2 times kx squared, not x. So x is d in this problem. That's how much it's squished. Equals m times g times 5 plus d. That's how high I'm going from 0. All right. And this is where I'm going to regret the decision to completely work out the problem. But I'm still going to do it. This is going to be a quadratic formula, y'all. If you can't see, you're going to see it eventually if you don't see it now. 1/2 times 1200 times the distance squared minus the mass. I'll put it on both sides. 0.015 times 9.8 times 5 plus d. Spread it on out, transfer it out, subtract this first number to the other side, subtract all that crap to the other side. Through the magic of bad handwriting, I'm going to have to shrink this stuff so it actually fits. Well, can't select that thing anywhere. All right, I'll fix it later. All right, so you get 600 d squared minus, I'm going to get a calculator. Thank goodness I didn't forget that one in my office, so at least remembered something. Oh, but it is dead. You can only ask for so much in life, right? That's all right. That's why I got my backup scientific calculator, which is much worse. We're just using suboptimal tools today, but we're going to get the job done. All right. 0.015 times 9.8 minus 0.147d minus 0.735 equals 0. And then you're going to do the quadratic formula. look, if I had my decent pen, I'd write out the quadratic formula, but the reality is it's going to be I'll try. It's going to be terrible. Negative b plus or minus square root. Ugh. My laptop moved. Square root of b squared minus 4ac all over 2a. So your b is the second term, your a is the first term, your c is the last term. You plug it in and you make a decision because it's going to give you two answers. Plus or minus. You got to make the decision of what it's going to be. And the answer, honestly, the way I make the decision, I know if we didn't account for that, it'd be 0.035, so this is going to be more than that. But yeah, try it out, right? It's good for your health. Always good to do a bit of quadratic formula in your life. There is no avoiding it in this problem. No getting around it, y'all. All right, so it spits out either 0.0351. That's one option. Or negative 0.0349. How do you choose the right answer? You can't compress a spring a negative amount. Like, we always consider the compression of a spring as a positive number. So, boom, that answer is not a possibility. There's your answer. Yay. All right, and your units chucked there at the end, meters. So there you go. Yeah. Yep, it's a good question. Why was there no potential energy due to gravity in the beginning? And this is where I'm going to need my mouse again, because it didn't let me move the picture without the mouse. Well, okay, I'm just going to go back to this slide. We started zero height. So we chose, you get to choose where your height is zero. You get to choose where zero position is. We made the smart decision to make our life easier. And we decided to make the initial position. Where do we want zero to be? You generally make zero either where you begin or you end, so you don't need to calculate the gravitational potential energy there. So here, where are we located? We're located at height zero. So mg times zero is zero. Yep. Yeah. So if you did the math for it, you only get gravitational potential energy if you're above zero or below. And if you're below, you do get a negative. That's important. Because if you're below zero, you need to have less energy than at zero. How do you get a smaller number than zero? You go negative. Yep. All right. So this is conservation of energy, y'all. Every single problem with conservation of energy is done this way. And I have now also remembered that I lied to you. Okay, I remember this before, but I remember to remind you all. The reason my pen is left in my office is because I was fixing a mistake. So I lied to you all last class. I mistaught you all. Shame on me. If we go back to, was it in this slideshow? It is. All right, so I want to point this out because I gave you all the wrong answer. This one. Find the magnitude of the force corresponding to the potential energy. And I said it was the second derivative. Wrong. It's the first derivative. So I have fixed it and I've uploaded it. So let me just walk through this. I'm not going to rewrite it all because I don't have the time. But I did upload this online. So the one I uploaded online has the correct thing. So work is the negative change of potential. Fantastic. So work is the negative change of potential. And I'm actually going to presenter mode so I can use a laser pointer. There it is. All right. Work is the negative change of potential. Awesome. Work is the derivative of f dx cosine theta. Awesome. Set them equal to each other. How do I get rid of the integral? I just take the derivative one time. By taking the derivative one time, you get du dx. The delta u goes up there. Dx goes on the bottom. Take the derivative. It cancels out there. So the derivative cancels out. So you're left with f equals this side, the derivative. And you just take the derivative one time. So f is equal to the negative. This is true, not the second derivative. So my apologies before y'all. I misled you. All right. And again, these are uploaded, so the right ones are there. But I wanted to point that out to y'all. Okay, where are we at time-wise? Let's see. Do I want to do that problem or this problem? All right. We're going to skip this one. I will upload the slides with this one worked out, but for the sake of time, we're going to do this one. I want to start talking about momentum today. A boy throws a ball of mass 0.25 kilograms straight upward with an initial speed of 20 meters per second. When the ball returns to the boy, its speed is 17 meters per second. How much work does air resistance do on the ball during its flight? First step, draw a picture. If there's a beginning and an end, it's useful to draw, it's just always useful to draw a picture. If you haven't seen that at this point, you will realize that at some point. Pictures are great, y'all. So try it out. Draw a picture. Beginning and end. Decide where you want 0 to be. Where you want y equals 0 to be. All right, so it's going to be a fairly straightforward picture. So initial, we're going to have a ball, and it's going upwards, 20 meters per second. And then we have a final. The ball returns to the exact same spot, but now it's going down, 17 meters per second. Now you get to decide, where do we want 0 height to be? Let's pick somewhere really convenient. Pick somewhere where we don't have to do a bunch of calculations. Let's just set where it starts and ends at 0 height. Then we don't have to worry about gravitational potential energy. You get to decide where y equals 0. Pick one that makes your life easier. Because at the end of the day, the change in gravitational potential energy is 0. That's always what. The first problem from this problem set stresses that you can change the value and it doesn't change anything in the problem. You can decide where 0 is. All right, make our beautiful list of givens. It's not going to look beautiful, but you know what? And I got rid of the eraser button here because I was like, I don't need it. My pen has an eraser. It did. It still does. It's just not with me. All right, so there's my mass. My initial velocity is 20 ms. My final velocity, if we want to be extra careful, it's negative. It's going downwards. It won't change anything in the problem. Step 2, we are solving for the work due to air resistance. Now, this is where I just call this WF. I call air resistance and friction. They're the same thing. They just look different, but they all slow things down. So if you want to put W air, that's fine by me. WF, fine by me. W smiley face, as long as you know what it means, fine by me. I don't care what you label it, as long as you know what it means. And this is where we're going to do our bread and butter equation. Anytime you see work and things happening, a beginning and an end, conservation of energy problem. EI plus the work done equals the final energies. And you all make decisions. What energies do I start with? What energies do I end with? You decide. There's right answers here, but try to figure it out. Yeah. Spend some time. This is the challenge in quotation marks. And when you're doing energy problems, that's just what you need to figure out. What do I start with? What do I end with? Yeah. So gravitational potential is how far you are from zero. We just start at zero, point the gravitational potential. Otherwise, you have to make it number 4. You have to say start 5 meters. But then you'd also add 5 meters. Yeah, so yeah. Yeah, so we go through our checklist. Do we have gravitational potential energy? Well, we very conveniently chose this thing to start at 0, so we don't. What's my distance from 0? 0. Ta-da, no gravitational potential energy. You could have chosen it to be down here on the bottom. You could have chosen the 0 to be below it, and then I would have started with some height, but I would have ended with the same height. So they would have just canceled each other out and made your life a little bit extra harder. All right, great. No gravitational potential energy. We defined it as 0. Make our life easy. There's no springs in this problem. No spring potential energy. But it's moving. So we got that type. So we do have kinetic energy. So what we're going to do is we're going to write this over here. So 1/2 times mv initial squared plus the work done by friction, i.e. air resistance, equals, at the end you ask yourself the same question. There's still no springs. I still end at y equals 0. There you go. And ta-da, we just derived the work kinetic energy theorem. Work equals a change in kinetic energy. Look at that. It all connects. Yeah. Yeah, when work is negative. Yeah, when work is negative, we lost energy to the environment. That is 100% what it means. If work is positive, you gained energy from the environment. Which makes sense, y'all. We lost energy. We're not going as fast. Where to go? To air resistance. You literally made the air molecules start moving around. It literally pushes air molecules out of the way and starts making them move. So they gain energy. Where did that energy come from? This system. So you lost it to the environment. All right. Step 4, plug in the numbers. So work due to friction is just going to be the change in these things. So 1/2 times the mass, which is 0.25. I do not have enough space. Oh, no. Reattach my computer. Y'all can try it out. See, there's the answer up here. You can see the answer is negative. Great. So 1/2 times mass times the final velocity squared. Now that's fine. You need to make certain you put your stuff in the right space. So 1/2 mv final squared minus 1/2 mv initial squared. That's just algebra. If you put your numbers in the wrong spot, you're going to get the wrong answer. And a positive work and a negative work are drastically different. So you got to be careful. So work due to friction equals 1/2. I'm going to pull out the masses so I don't have to write as much. Times negative 17 squared minus 20 squared. I just pulled out the masses and I pulled out the 1/2. So I didn't have to write as much because I don't have much space here. All right, and ta-da, we get the right answer. Woohoo! Don't forget your units. It is negative because friction, air resistance always take away energy. You lose energy to those things, to the environment. You literally move air particles out of your way as this ball is moving. And that steals energy from the system. So there you go, y'all. There's energy. It's a very straightforward thing. We are going to jump into momentum. So we're going to keep on rolling. You know, we got 30 minutes left in class. And the reality is, the more time we have, the more problems I can solve, the slower I can go, like, the more careful we can be, all that kind of jazz. So, all right, I'm going to leave this for a few more seconds, and then we're going to move to momentum. So in case you were jotting anything down, I want to move too quick. Yeah, we're back to it. But the math is really simple. Like the equation is really simple.
Aren't there two collisions?
Yeah. Of course. It's good for your health. All right. Your vacation in Scalar City is over. Yeah. We're back to vectors, y'all. It's good for your health. Okay. So, boom, boom, boom. Collisions and linear momentum. Momentum is incredibly useful. Momentum is going to be like energy where it's made up. Momentum is one of those things where if you calculate it at the beginning and you calculate it at the end, they're the same. And that's the benefit of momentum. It's super, super useful. Any collision that possibly happens, whether they bounce off each other, get completely stuck to each other, or kind of in between, you can use momentum for. And so like the example that's like shows how useful this is, if you have an asteroid and it splits into like 10 chunks that fly in all sorts of different directions, if the asteroid initially isn't moving, it has a momentum of 0, and if you add up all the momentum of all the flying pieces, they also will equal 0. So we're going to do some examples of that where it's you can just do so much with it. If something explodes and you know the velocity of one piece, you can find the velocity of the other piece. It's good stuff. It doesn't matter why it exploded. It doesn't matter what made it explode. It didn't matter how long the explosion took. It didn't matter how it broke up. As long as you account for all the pieces, it all equals what you started with, which is really cool. It almost feels like magic in some ways. You'll see what I mean. All right. So we're going to tell you what momentum is. I'm going to use a very hand-wavy definition because momentum, like energy, is one of those that the better you understand it, the more it's like this is made up. But it's still useful. We're going to talk about impulse. And then we're going to talk about conservation momentum, which is so, so, so useful. You'll see. Just for now, trust me. All right. Vectors are back, which immediately leads us to the next bullet point. You got to split your x and y's up. All your x's are together. All your y's are together. If you mix them together, it doesn't work. Don't do it. It's real bad. And then kinematics equations are going to kind of show up in here because we're going to use them. They're always handy. Anytime you have stuff moving, kinematics equations are useful because they let you relate position, velocity, acceleration, and time. They're the bread and butter kind of this class in a lot of ways. All right. So yeah, just don't forget about XY independence, y'all. Okay. Now, this question is a show that most of you, even if you haven't taken physics before, you probably know what momentum means. The everyday use of the word momentum is pretty accurate to the scientific definition. Like the intuition is basically the same. So what has the most momentum? A football player running, a parked car, a baseball getting tossed at you by a human being, or a car going 10 meters per second, which is about 20 miles per hour, give or take. All right, we'll go 10 more seconds. Go with your gut. In 5, 4, 3, 2, 1. All right. There's still random people responding. There we go. All right. Look at that. Hey, this looked almost identical to my first class. The majority of you are correct. And here's where I'm going to introduce my hand-wavy definition that you may or may not have been using. My hand-wavy definition of momentum is what's the hardest to stop. That's kind of like how hard it is to stop something. That's my hand-wavy definition of momentum. So if you look at these scenarios, a car going 20 miles per hour is the hardest for you to stop. You're not going to. That's basically the punchline there. You try to stop a 20 mile per hour car, it ain't going to stop. It'd be kind of difficult to stop a football player running, but it's not going to you're going to do better than a 2,000-pound vehicle going 20 meters. It's just not happening. And then the rest, same old, same old. You get hit by a baseball, you're going to stop it. It might hurt, but you can stop it. So anyhow, there's momentum. Here it is defined. My hand-wavy thing, how hard it is to stop something. If you look up definition of momentum, you basically, a lot of them just say mass times velocity. Because remember, it's kind of a made-up thing. Momentum, like energy, it's just one of those things that's conserved. Why? You can connect it to forces and kind of derive it from there, kind of, sort of. But the reality is, it's just one of those things like energy that's conserved. Just one of those weird quirks of the universe. The symbol is P, which is not ideal. The word momentum, if you had a choice, what would you choose for momentum? Yeah, it's already taken. M's taken. M's used for mass. So, we only have so many letters in the English language. There's a reason these Greek letters, you literally just write out the English letters at some point. The reason it's P is some Latin word that starts with a P, which means something that's, my TA looked up this morning and I forgot already. Feel free to look it up for yourself, but it comes from a Latin word, something about motion in some capacity. It's interesting. Feel free to. Yeah. It's not pendulum. It's a word that you probably have never heard before. Yeah, it's some weird Latin. Feel free to look it up. If we have some time, maybe I'll remember. Feel free to look it up now if you want. You can shout it out to me. All right, the units for it. Yeah. We are not going to do oscillating motion. Is that good? That's good? Okay. I used to cover it, but I've replaced it with center mass. All right. The units. Where do the units come from? The math. The units are really straightforward. The equation for momentum is mass times velocity. What's the unit for mass? Kilogram. What's the unit for velocity? Ta-da! You all derived the units for momentum. Because again, it's kind of it's a quantity you just calculate. So the units just come from that. If you forget the units on a test, just derive it yourself. It'll take you 5 seconds. Less than that. All right. The direction of momentum is the same as the direction of velocity, which makes sense because mass is not a vector. So you get a constant times a vector. Great. All right. Very challenging question ahead. What's the momentum of a 0.5 kilogram baseball traveling at 10 meters per second? Yeah, I know. Brutal. Y'all got a whole minute for this. All right, 5 seconds. 10 seconds. Oh, glitches, that's fair. All right. 5, 4, 3, 2, 1. All right, really straightforward problem, y'all. Mass, velocity, P equals mv equals 0.5 times 10 equals 5. And then the question is, did you put the right units? There is right units. Joules is energy, not momentum. It's good to keep track of these things. All right, fantastic, nice and easy, nice and straightforward. Nope, wrong one. Oh, man. Now I got to exit. There's no eraser on this thing. Draw, erase, go away. All right, onwards and upwards. Okay. What's the point of momentum? Why do we care? Two things. We can use it to find velocities of other objects. It's a conserved quantity. As long as you don't have stuff like, as long as you don't have non-conservative forces acting on it, i.e. air resistance and things like that, as long as there's no air resistance or friction going on in your problem, momentum will be conserved. We'll see that. That'll be kind of actually a lot. That's what we'll start covering next week. The other one is this one we're going to start using it for today, is we can use it to find the force. It's another way of finding the force acting on an object. We now have three ways to find the force acting on an object. We got momentum, we got F equals ma, and we got work equation. So, that's a foreshadowing. All right, this is straightforward. A collision is when two things hit each other. It matches what you'd expect, but we're going to, good to define it. Collisions when two things interact by means of a force. Nothing surprising there, exactly what you expect, but again, just one of those vocab words that is going to show up, so might as well define it. Okay, all right, this derivation, lots of things here. We are going to look through this one piece at a time. Do not look at the whole thing. Start at the top, and you're going to see that you can derive this for yourself. F net equals ma. Hopefully you're cool with that. F equals ma. Now, what's the next step? We replace A with dv dt. That's something from like the second week of content. The definition of acceleration is the derivative of velocity with respect to time. Fantastic. Great. This is done. F equals mv dt. That's all we needed this for. We're going to set that aside for now. Okay. Now we're going to look at momentum. I just told you that momentum was m times v. It is what it is. So what? Well, if we decide, whatever I do to one side, I'm going to do to the other. I'm going to take the derivative of time of both sides, just for funsies. It's just like adding 2 to both sides. Whatever you do to one side, as long as you do it to the other, you're allowed. What's the benefit of that? That changes, this to dp dt. Nothing surprising there. That's just literally the definition of taking a derivative. And then this one turns into this. Mass is a constant. We're not going to have mass change with respect to time. We're going to say it's a constant mass. So then I take the derivative of velocity with respect to time. Okay, so a bunch of small steps. What's the benefit of all this? This and this are the same thing. So let's just kind of write that to the side. So we have F equals m dv dt. We now have dp dt equals m dv dt. If A equals B and B equals C, then A equals C. That's what we did here. We have F equals mv dt. We have dp dt equals m dv dt. So if they both equal the same thing, they equal each other. A equals B, B equals C. So what color are we going to pick for that? A nice purple. All right. These two things equal each other. Ta-da! How do I get rid of a derivative? Plop that dt to the other side. Take that dt, kick it to the other side. How do you get rid of a derivative? Integrate both sides. Long story short, this is the punchline. The change in momentum. So just to show you all what happened in these last steps, I just integrated both sides. Okay. The change in momentum equals the integral of force with respect to time. And this again might look like some nonsense. We're going to do some problems with this and show you all this is incredibly useful. If you know the change in momentum, you can very easily find like the average force acting on an object. If you just find how like the velocity change, which makes sense, this is just a rewritten of Newton's first law or Newton's second law, but it's called impulse. There is a variable for this. It's called J. I don't know why they came up with a variable for it. On the formula sheet, I give you all J equals delta P equals this thing. But it does have a fancy name called impulse. And if the force is constant, you can pull it out of the integral. Or if we care about the average force, same thing, we can pull it out of the integral. And the integral of dt is just t. So if f is constant, you get this bottom equation. If the force is constant, you get this equation, which just says my change in momentum equals the force times time. Super, super nice. Super, super handy. So we'll apply this to a variety of situations. We'll do a few more clicker questions. But this is one use of momentum. And honestly, this is just rewriting Newton's second law. You can kind of look into that on your own if you want. All right, so let's apply this to a situation to see how this relationship is useful for us. How this can help us understand things that otherwise you might have to think a bit more. All right, if you get in a car crash, in which case will your face experience a greater change in velocity? Is it if your face hits the steering wheel, your face hits an airbag, or your change in velocity is the same in both situations? If you want, make up numbers for your initial velocity and your final velocity. That's going to help you. I don't think... And the key to this, y'all, final minus initial. Decide how fast you're moving at the end. Make up a number for how fast you're moving in the beginning. All right, we'll go 15 more seconds. And 5, 4, 3, 2, 1. All right. So, let's say you start at 60 miles per hour. Let's say that's 27 meters per second. That's your initial velocity. My final velocity after my face hits something, I don't care what you're hitting, you're stopping. Notice I didn't label the situation here. So the answer here, I don't care what stops you. You're changing velocity. You're going from 20, you're moving, and then you're not. So this is just kind of reminding yourself, this is Change in velocity, you don't care about why you're stopping, but you were moving and now you're not, and it's going to be the same no matter what. Your face was going 27 meters per second. Your face hits something. It stops moving. All right, why did I ask this question? Well, let's explore the next thing. So let's kind of then move forward to the next situation. If you get in a car crash, in which case will your face slow down over a greater time? Steering wheel, airbag, or both happen over the same time? Oh, I gotta hit the button. Boop. Over a greater time. Which one happens over a greater time? All right, we'll go to 1 minute on this. And 5, 4, 3, 2, 1. All right, greater time, it's going to be the airbag. It's squishier, y'all. It's going to slow you down over a greater time because it's nice and squishy. If you hit something hard, that's real quick. So, let's put all this together, y'all. Let's put all this together. So why is this useful? So if you get in a car crash, in which case will your face experience the greatest force? Before I remember the equation, y'all, F equals change in P over change in time, which can be rewritten as, again, you all could have answered this question from the get-go, but it's to show you how this equation reveals things to you. Yes? I think in general the airbag, you still hit your face forward on it. I don't think it pushes your head back that much. I'm just thinking of videos of seeing the airbag. When the collision happens, you're moving forward still, and so you will run into it. It might push you back. Either way, you're coming to a rest at 0. The airbag is interacting with you over a greater time no matter what. For sure. If it's not, the answer to this will be wrong. Oh, yeah. All right, we'll go to 1:30, so 15 more seconds. The answer is going to be what you expect. It's not a trick question. You could have answered this without taking my physics class. In 5, 4, 3, 2, 1. All right, so let's do this with physics. Delta V is the same. Delta V is the same. Delta T here is larger. Delta T here is smaller. If I divide by a big number, I get a small number. If I divide by a small number, I get a big number. It's what you expect, y'all. What's going to hurt your face the most? Hitting a steering wheel. But now you see how it connects to this equation. The change in momentum over the change in time gives you the average force. Gives you the average force, not the instantaneous, unless it's a constant. So this relates to every single collision that can ever happen. This is true. So one more connection for y'all. Last connection, and then we'll solve a problem next class. The egg drop challenge. The egg drop challenge is a challenge in how do you make an egg not break. Assuming all eggs are the same, they can withstand a certain amount of force without breaking. That's the whole challenge. How can you reduce the force that the egg experiences? That's basically the challenge, but simply, there's some video recently about hydrostatic pressure and all that and whatever. But in general, you want the force to be as small as possible. Now, something really interesting about the egg, you can test this for yourself at home. I did it in high school. You might ask yourself, does the orientation of the egg matter? It does not. As far as my very, very basic experiments, so in my high school class, we took an egg, and then we just kept stacking weights on it until it broke. So we did it upright, and then we put it sideways, and we kept stacking weights on it until it broke, and they both came with the same amount of weight. Which is really interesting. You can test that for yourself at home if you have two eggs that are identical enough. Just literally start putting weights on them, put like paper or something, and see how much paper it takes to break it in one orientation and change it. So the shape of an egg is really cool. Its structural integrity does not depend upon the orientation. That's cool. Anyway, so how do we reduce this force? You got two options. Either make your delta V smaller. Make your delta V smaller, or make your delta T bigger. According to this equation, that's the only two ways to decrease your force. So, options, you can put a parachute on it. Then it's going to be going slower when it hits the ground. That works really great. Or provide a bunch of cushioning so that you increase your delta T. There's great physics behind this that you now get to see that everyone else, they kind of just go intuition. It's largely good, but man, it's good. And thanks for the fit. Yeah. All right, that's what we're going to do next time.